Hello everyone. In today's session, we will see which are the regions in which every harmonic function can surely have a harmonic conjugate. And this is clearly stated in theorem 2.30, which says that suppose if we are having G to be the whole complex plane or some open disk in the complex plane, and if U is a harmonic function defined in that G, then you will definitely have a harmonic conjugate. So, what is the peculiarity of this whole plane, whole complex plane and open disks is that both of the regions are simply connected. That means if two points are taken inside the set, the line joining those two points will be necessarily inside the region. That is a simple definition of simple connectedness. So this is a peculiarity of these two regions in which is mentioned in the hypothesis. So before moving on into the proof, let's just recap what is Leibniz rule for differentiating under the integral sign. Okay. Suppose if f of xt is a continuously differentiable function, that means its partial derivatives are existing and they are continuous. Suppose if a of x and b of x are continuously differentiable, then d by dx of integral from a of x to b of x f of xt dt is equal to f of x comma, instead of t we are having b of x into the derivative of b of x minus f of x comma a of x into the derivative of a of x plus integral from a of x to b of x dou by dou x of f of x t dt. And suppose if this a of x and b of x are constants a and b, then the same equation will become d by dx of integral a to b f of x t dt is equal to this b dash of x and a dash of x will be 0. Then that just leaves us with the third term, which is integral from a to b dou by dou x of f of x t dt. So this is what Leibniz rule for differentiating under the integral sign says, and this is used in a theorem as we move on. Okay. Suppose G is equal to B0 of R. Okay, B0 of R in the sense open ball centered at the origin 0 with radius capital R. And this capital R can be, capital R is strictly positive and it can even take the value infinity. That means we are giving the possibility of the complex plane also for this B0 of R. So every open disk is included as well as the whole complex plane is included. Suppose U is a harmonic function in G. Okay. How to move on into the proof is by having the aim. We are going to find a harmonic function V such that U or V are satisfying CR equations. We definitely know that if U and V are satisfying CR equations, that will imply that both of them satisfy the Laplace equation as well. That means both are harmonic. Okay. So this is the idea of the proof, how we move on. So first we define the function v of xy, which is equal to integral from 0 to y, the first derivative of u with respect to x of x comma t dt plus phi of x. Okay. So we know that this function u is satisfying the Laplace equation because it is harmonic. So it definitely has first partial derivatives existing and they are continuous, right? So the existence of this is guaranteed and we are integrating them from 0 to y. Note that the region, open disks or the complex plane are chosen because we have to make this v of xy well defined, and this v of xy can be well defined only if we can integrate along this path, only if it is the region is a simply connected region. That's why we have chosen it to be either open balls or the whole complex plane. Now, now our aim is to find this phi. Okay, we define this v of xy which is equal to this and called it star, equation star, and we are going to find this phi such that u and v are satisfying CR equations. We said that was our aim. So definitely since they are satisfying CR equations, we know the second CR equation which is uy is equal to minus vx, that means vx is equal to minus uy, right? And what we are now going to do is, we are going to differentiate this equation star with respect to x. So consider dou by dou x of v of xy. Okay, that is equal to dou by dou x of integral from the guy sitting here in the RHS. We are taking the first derivative of these guys with respect to x. So this will be dou by dou x of this term plus the derivative of e of x with respect to x. That will be the usual derivative because phi of x is only depending on x. We can call it d by dx of phi of x or phi dash of x. Okay. And for this first term, we need to use the Leibniz rule. That's why we had mentioned it before. We are using it often while moving on into the proof. So we are differentiating with respect to x, right? So please check out our Leibniz rule here. See, uh, and we are here we are differentiating with respect to x, and the limits are coming in terms of x, right? So, but in our case, we are differentiating with respect to y, and we are differentiating with respect to x, but the limits are not depending on x. Okay, so they are behaving as constants. So we'll have a particular case. So we'll just be left with this term. Fine. So here you will be getting integral from 0 to y, dou by, just take this dou by dou x inside, dou by dou x of ux of x comma t dt plus phi dash of x, and this is nothing but uxx, right? And we know that u is a harmonic function, so we know that uxx plus uyy is equal to 0, so this uxx can be replaced by minus uyy. Minus is taken out, and that is nothing but dou by dou y of uy, right? Okay, and we are integrating this with respect to y. So note that we are in, no, yes, yes, we are integrating it with respect to t, and the limits are from 0 to y. So when we integrate, what are we going to get? This dou by dou y will vanish, and we are left with this uy of x comma t, and that is varying from t is equal to 0 to t is equal to y, fine, plus phi dash of x. Okay, that is equal to, apply the limits, we get minus of uy of xy minus uy of x0 plus phi dash of x. So what we now basically, where did we start with? We started with dou by dou x of v of xy in the LHS. So to summarize, what we got now is dou by dou x of v of xy is equal to minus dou by dou y of u of xy, right? Plus uy of x comma 0 plus phi dash of x. Okay. But we assume that they are satisfying the, especially we said that we started with the second CR equation which said Vx is equal to minus uy, right? So as we are assuming that, we know that these guys will cancel out, and what it gives us back is uy of x0 plus phi dash of x is equal to 0. That means phi dash of x is equal to minus uy of x0. Okay, and integrate with respect to x, you get phi dash of x in the LHS, and that is equal to minus integral from 0 to x. So 0 to x uy of x0 dx, right? We are integrating with respect to x. So this term will completely come in terms of x, right? So in order to avoid confusion, I am going to give, instead of x inside the integrals, I am going to give s. Okay, to avoid confusions. That means we got phi of x is equal to minus integral from 0 to x uy of s0 comma ds. So we obtained v of xy is equal to integral from 0 to y ux of x comma t dt minus integral from 0 to x uy of s0 ds. So we started with a u, which was harmonic and ended up with a v. Okay, and we know that it satisfies the CR equations. That's how we formulated it, and we know that we applied that Vx is equal to minus uy, right? And also it is necessary that we have to verify that Vy is equal to ux as well as Vx is equal to minus uy. We have to just verify for our conclusion. So that I'm going to leave it to you. That is a question to work on, which is to check the CR, just check out to verify the CR equations, that is Vx is equal to minus uy, Vy is equal to ux. We know what is V now, right? So differentiate it with respect to x and differentiate it with respect to y and find out whether that is equal to minus uy and ux simultaneously. And of course, you will have to use Leibniz rule, which was mentioned when we started the proof. Uh, yes, we had already mentioned why we required the whole complex plane on the open disk. That was to ensure the simple connected nature of the region, and that will make our V of x well defined. Otherwise, it is not able to. It will not be able to define like that. So that's all for today, and thank you for watching.